Also you can come closer, no problem. Just I think the camera, don't block that camera. You can come from this side. Yeah, if you wish. आप बैठ सकते हो, मतलब खड़े होगे तो ब्लॉक हो जाएगा वो. हाँ बस ठीक. यहाँ दिखेगा ना, लेकिन कैमरा वाला नहीं दिखेगा. So after this you guys can come, once my recording is done you guys can come and do the experiment in front of the camera, no problem. Okay, and I gloves है ना sufficient सबके लिए. हाँ, ready? Rishita ready? Ruchira ready? Okay, good morning everyone. Welcome back to day 4 of Gyan. So today we are going to do a hands-on experimental session in which we will show you how to develop a glucose sensor for your applications. Over the past few days you have looked at, during the lectures you have seen how what are the different methods of implementing or developing a glucose sensor. Today we are going to show you experimentally in real time how to do it. Okay. So for today's experiment we have with us a PCB based sensor. So this sensor has a reference electrode at the center. This will be a 3 electrode system. Then it is surrounded by a counter electrode, semicircular counter electrode, and then surrounding the counter electrode are the 4 reference electrodes. So today we are going to do one channel recording. If you wish you could also do multi-channel recording using this PCB based sensor. Moving on, we also have a potentiostat with us which will help us do different types of characterization and functionalization methods. The chemicals that are required for today are as follows: potassium ferricyanide solution, we have glucose oxidase and phenol dissolved in PBS 100 millimolar. Before today's session we have mixed 6.6 milligrams of glucose oxidase in 1.5 ml of PBS and 0.705 milligram of phenol in 1.5 ml of PBS. So moving on, we are going to start the experiment by checking the consistency and fidelity and stability of the working electrode. For this we will be using the potassium ferrocyanide as a redox reagent, and we are going to use an external platinum based counter electrode to do the working electrode check. So before we start electrochemical testing of the working electrode, first we will do just a connection test to make sure that the PCB based electrode is properly wired. So for this we will be using a multimeter and we will do a connectivity test. So the beep actually tells us that the electrode is properly connected. So as you have seen on the screen, the testing is successfully done. So now we will move on to test the working electrode electrochemically using cyclic voltammetry. So for this we will be using a pipette to draw out the potassium ferrocyanide solution. we will ensure that when we are dropping the potassium ferrocyanide solution on the working electrode, the solution covers the entire area of the electrode and there are no air bubbles on the working electrode or the counter electrode or the reference electrode. So, if you can see closely, you will see that there is a platinum based external counter electrode that is placed in touch with the solution and the solution is in touch with the PCB based electrode. Yeah, 4 scans we can do. So, now very shortly we will be setting the parameters for the cyclic voltammetry on the software for the potentiostat. You will see it very shortly. We can switch to the screen. So, on the screen now you see that we are trying to connect to the potentiostat. Once we will try again. So, now the potentiostat is connected to the software. Now we will be setting the CV parameters. So, please pay attention to the screen. So, we select cyclic voltammetry. So, this is just, since this is just a diagnostic step, so we are setting the number of scans at 15. Then we will set the voltages, sorry 3. So, if it had been a functionalization step, we would have actually increased the number of scans. So, E begin is set at minus 0.5, minus 0.1 volts. And the other voltages are at, the positive maximum is at 0.7 volt and the negative minimum is at minus 0.5. So, your voltage will sweep from minus 0.5 to plus 0.7, the starting voltage will be minus 0.1. So, now we are ready to start the CV scan. So, as you have seen earlier, it is a triangular voltage sweep that is performed between the working electrode and the reference electrode, and the current is measured through the counter electrode. So, you can see on the screen CV has started. This is the oxidation peak. First scan completed. We have oxidation and reduction peaks. So, it will continue like this 3 times, performing 3 scans. The shape of the CV curve indicates that the working electrode is working okay. The oxidation and reduction voltages can be noted down for further analysis if you wish. So just to repeat, for this CV we have used E begin at minus 0.1 volt, EVX1 at 0.7 volt, EVX2 at minus 0.5 volts. The scan rate was 0.05 volts per second, each step was 0.002 volts or 2 millivolts, and the number of scans were 3. Completed? Complete. So now the first step for checking the working electrode is done. The curve tells us that the working electrode is fine, and this working electrode, just to remind you, is coated with platinum. So the second step would be to wash the potassium ferrocyanide, and then which is the cleaning step. So for this cleaning step we will be using DI water. After the cleaning step we will do electropolymerization to deposit glucose oxidase on the surface of the working electrode. So when you will all do the experiment live, you can note down the oxidation potential and reduction potential. So we will proceed with the cleaning of the working electrode with DI water. First we will remove the fluid using pipette, then we will wash it with DI water. So the detailed protocol we will actually give it to you at the end of the course. You can have it and repeat it. We can switch to the cleaning part. Huh? Switched. Okay. Stabilization and GX. Okay, so we will now proceed to the GX electropolymerization step. You can see on the screen when we will be depositing the GX phenol PBS mixture on the electrode surface. Then we will again run a cyclic voltammetry step to electropolymerize the electrode. So this step will take some time to complete because we will be using slightly larger number of scans. So while doing this, we have to ensure again that when we are depositing the GX phenol mix on the electrode surface, there should be no air bubbles and the solution should cover the entire electrode completely. Try to make sure that there are no air bubbles. Can we switch to the screen? Yeah, done. Ready? So now we are going to the we are going to set the CV parameters for the electropolymerization step. We go to select CV, then we will set the number of scans, which is 15. Scan rate will remain same, E step will remain same. So as you know, this is a single channel potentiostat. We can do one working electrode at a time. If it had been multi channel, there is a chance of doing and functionalizing all the or electropolymerizing all the working electrodes at the same time as well. So for here, for demonstration purposes, we will be doing it for one working electrode only. Ready? Parameters are set, E step, E begin and all that. E begin. So E begin is at minus 0.1, EVT1, EVTX1 is 0.7 and EVTX2 is minus 0.5. So we are going to start the CV scan. Please start the scan. Ready? Please start the scan. So this step is going to take some time because there are 15 scans. So we'll have to wait patiently and we'll monitor the CV curve. If we observe that there is some noise or instability on the CV curve, we'll have to stop and fix it. The CV curve for electropolymerization will look slightly different from the CV curve that you have observed during the working electrode checking process. One scan completed. Now second scan, 14 more to go. We have to wait patiently until all the curves are done. So ideally, if your CV is working properly, if your all the electrodes are working fine, then they should overlap more or less. All the scans should overlap. So here they are overlapping, as you can see, which is a good sign for us. So this is what type of sensing? Enzymatic or non-enzymatic? Enzymatic, because we have used glucose oxidase enzyme. So there are two more steps to go. Once the CV is completed, then we will do a stabilization step, and then last step would be calibration. So in calibration, we will check what is the linear range of our sensor by using known concentrations of glucose. So broadly, in all sensor development, the steps are same. The first will be, so electropolymerization is called as the functionalization step, where you functionalize the layer of the electrode, working electrode. Functionalization is followed by calibration. Okay, so there may be a stabilization step depending upon the protocol and the mechanism involved. So on the bottom of the screen, you can see the potential is changing, time is, so we have until now, you can see the time also. So after the functionalization is completed, or the electropolymerization is completed, we will proceed with the stabilization step, and once the stabilization is done, during the calibration we will be using the counter electrode that is located on the PCB. So if you remember, Until now we are using the counter electrode, the platinum based external counter electrode, but once our functionalization step is over, we will be using the PCB based counter electrode. So, until now we are using the reference electrode which is on the PCB, working electrode on the PCB, but counter electrode external. But now we will be in the calibration phase, we will be using the counter electrode on the PCB. So, when you are doing it in the field, let us say you are going to test glucose using this sensor, then you will be using all the electrodes that are on the PCB. So, I thank the participants for their patience and the volunteers who are doing the experiment, hands-on experiment, Rishita and Ruchira. And during calibration we will be using amperometry. So, the sensor reading will be taken using amperometry. Okay. So, you can see how various steps are used CV for functionalization, CV for testing, and then amperometry for reading or measurement. One more scan remaining. So, as you can see at the bottom of the screen towards the left hand side, the time is reducing, as the scan is progressing, the time, you can see the change in time and voltages and current, and they are making the CV curve. And you can also see the different scans. So, each legend at the bottom is one scan, one line is one scan second. So, we have 15 scans, probably this is the last scan, I guess. Three more scans. I haven't counted. So, one more thing to note here as well is, one is the CV curves are more or less overlapping, but they will overlap in such a way that the area within the curve, area under the curve will reduce gradually. So, as electropolymerization is taking place, as the surface is being coated, the area will get under the curve will get less. So, if you wish, 15 scans is something which we have seen works well. If you want for further If you want to make the sensor stronger, or if you want to ensure that the electropolymerization is done properly, then you can go for higher number of scans as well. Okay. So, in the interest of time we have kept it 15, but if you wish we can go up to 20, 25 as well. Complete? No? Last? Screen. Then we sweep there. So, this PCB based electrode has been given to us by our expert, foreign faculty, guest faculty who is visiting us under this GYAN program, Professor Sanjeev Sharma, and we acknowledge support from GYAN and we thank GYAN for the support. Complete? Complete? Done? So, now we will proceed to stabilization step. Before that we can wash off the GOX phenol mix from the electrode surface. You can use so Rishita is actually saving the curves for future reference. You can also load this exact protocol by opening this file again and rerunning the CV curve. So, you do not have to enter the parameters again every time you do a new sensor. So, you can simply load the parameters from the previous files. Can we switch the screen? The lab, huh? Yeah. So, we will go for washing. Yeah. So, for stabilization we will be using PBS solution and amperometry. As you can see on the screen, we will now replace this. We will now replace the previous GOX phenols mix with the PBS solution. Again, when we are dropping the fluid on the PCB sensor, we have to make sure that there are no bubbles and the solution covers the entire all the electrodes. So, once we are done with the calibration, you all can also come and do the calibration. If you want to do the functionalization again also using the same electrode or new electrode, you can do. We have up to around 10 to 15 PCB electrodes. So, if you want to do yourself also, it is fine, no problem. This is PBS. Yeah. So, we are going to now put PBS on the electrode surface. Ishita is applying PBS on the electrode surface. One more very important thing to remember is when doing these lab experiments, please use the gloves, because if you touch the sensor surface with bare hands, it might spoil the sensor. So, in point of care diagnostics, generally we combine microfluidics with these sensors, so that the microfluidics actually ensures that the fluid is properly covering the sensor. So here we are doing it manually, we are ensuring that it is covered properly, but if you have, let's say, a glucometer, if you look at the strip, you put a drop of blood, and that blood is drawn through the microfluidic channel, and it covers the sensor properly. So that process is automated using microfluidics. Ready? So now we are proceeding with the stabilization. You can show the screen. So here we will do an amperometry step. So amperometry, as you can see on the screen, it says amperometric detection. We have to set the oxidation potential. Please. Yep, you can set the potential. You already set. So the oxidation potential is E is equal to 0.7 volts. Yeah, we can start the 600 seconds. 600 seconds. We'll be running it for 600 seconds. So we'll be running the stabilization step for a bit long. So it's around 600 seconds. So it will take long time to complete. Approximately 10 minutes, right? Not approximately. So this is amperometry. So in amperometry, if you remember from your classes, potential is fixed. It's not swept. Since CV, the potential is changed in a triangular waveform, but here it is actually fixed, and the current is observed. So ideally this current should stay stable, flat. Since we are doing, there might be some disturbances due to recording equipment and stuff, due to noise. But overall, more or less, it will look like an exponentially decaying curve. So this is very short duration. As we keep it running for 600 seconds, there is a little bit of disturbance due to various factors. So here, are we using the so we are using the external counter electrode. In the calibration step, we will be using the PCB based counter electrode. So what is the oxidation potential that we will be using during the calibration phase? 0.7. And what is the current that we are getting right now? 5 microns. 5. Huh? It's increasing. Yeah, we're not sure why it is increasing, but we will check in the calibration step whether the curve is linear or not. So if it is non-linear, then probably we have to repeat the measurements, or we can see what happens. Okay. But more or less, this is the process. Yeah, it will take around 10 minutes to complete. So in the meantime, we'll pass around some sensors if you want, maybe some CGM sensors. If you wish, you can have a look. Those of you who have not seen the CGM sensor, you can have a look at it, because you can pass. If you want to have a look, you can look. So there is the electronics, the PCB. You can see there is a small battery there. These sensors last up to 14 days in the body. These sensors also follow the enzymatic method. That is a connector, and that actually there might be some polymer electrode attached to it, right? So that is, so if you look, there are 3 points, 3 dots on the polymer electrode, right? So those are the 3 electrodes. Now what they have done is they have combined all 3 electrodes in a single polymer. That is, so instead of having 3 separate electrodes, they have managed to combine it in one, so it's convenient. That's part of their technology. There might be some IP behind it. We are not sure how they have done it. What's the time? 250 seconds completed. 300 seconds, almost half. No, let it run. Generally ampermetry curves, if you look at, you have a start and then it goes down and then stabilizes, but maybe due to noise it's not stabilizing, it's rising slightly. Yes. Oh, maybe due to noise, wind. Yeah. 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 What is the time? 380. So the sensor that I passed around, they are called as factory calibrated sensors. So what they do is actually they do the calibration step in the factory, and they know exactly how long the sensor will last without calibration, what is the range within which the sensitivity. So once you implant this sensor inside the body, there will be immune reactions as we discussed earlier, and then the sensitivity will decrease with day. Okay, so they know exactly how to model that relationship with respect to day 1, day 2, day 3, from day 0, how much the sensor degradation is happening, and accordingly they can actually adjust the sensor reading. So here you can see what is the what is on the y-axis, current, right? So during the calibration phase, when we look at the current for different concentrations, we can find out a relationship between the current and the glucose concentration. So the slope of the straight line will give us the sensitivity. Okay, so it will tell us how much microamps current or nanoamps current will change based on changing, let's say, 1 millimolar concentration. Okay, so that relationship is there. So you get sensitivity in microamps per millimolar or nanoamps per millimolar, and then when you are implanting the sensor and you are doing the reading, you will get, let's say, x microamps or x nanoamps. You multiply this value with the sensitivity and it will give you the millimolar concentration. Okay, so this sensitivity, microamps per millimolar, let's say on day 0 it is x, it will degrade with from the day, so it will be x minus something. So that factor, degradation factor, in factory calibrated sensors, they have a rough idea of what is be the degradation factor with day, so they can actually adjust their reading accordingly. Okay, so these sensors nowadays are factory calibrated sensors. Previous CGM sensors, there are a couple of companies which wanted their patients to actually, if they are using CGM, they wanted their patients to calibrate the CGM in a way that they will ask them to do a finger prick reading, draw the blood, measure using a glucometer and enter that value in their app. So they will do the adjustment there. But nowadays, because it is inconvenient for the patient to take the reading twice, and it kind of defeats the purpose of using a CGM sensor, because anyway we are doing this spot measurement again. So that's why more and more the trend is towards going towards this factory calibrated sensors, where you don't ask the patient or the user to do frequent calibrations. Okay. So here we will be doing a 4-point calibration, right? 4 or 5-point, right? Yeah. So we'll 4. So we'll be using 4 different known concentrations of glucose, and we'll measure the current. Then we draw a straight line, and then we find out the sensitivity. That is the last step. Complete. Stabilization is complete now. We will wash off the PBS and proceed with calibration. That is the last step, and it will tell us whether our sensor is working or not. It will tell us whether our functionalization was done correctly or not. Visibly it looked correct because looking at the CV curves, but here we will get verification, the final verification. And the calibration will also tell us what is the linear range of our sensor. Kaushik, can we please switch to the screen, this one? Okay. Experiment. Are you cleaning or cleaning? Okay, so cleaning is being done. So you can wash it with DI water also before, if you wish. It will be better to wash with DI water and then put the known concentrations of glucose. So what are the concentrations of glucose that we have here? No glucose, right? 0 millimolar or no glucose. Then 2.5 millimolars. Then 5 millimolar. 7.5 millimolar. Then 5 and 7.5 millimolar. So 2.5, 5, 7.5, 3 concentrations, and 0, which means no glucose. You can see on the screen all the solutions. So this one is 0, okay, no glucose. Is just PBS, just PBS. I think there are air bubbles. Can you do the pipetting again? It's fine. Okay. So make sure that you are covering the entire surface of the electrode. Okay. So here we don't need to take the reading for 600 seconds. If you take for 1 minute also, it's fine. 30 seconds is also fine, just to get the current value. Ready? Okay, you can run it. Same parameters, same oxidation potential. Wait, we are using the right now we are using. So can you show the screen? The experiment is being shown. So you can see there are no counter electrodes. There is no platinum counter electrode. We are going to use the counter electrode on the PCB. Okay, you can start. You can switch to the laptop. starting now. So at the end, we will actually look at the current values. You can please note the current value. This is for 30 seconds, right? There is a bit of instability, but we'll see. If the sensor is not working in this session, then we will do the same experiment, repeat it, maybe debug it in the next session and try to make it work. Okay. It's around 57 microamps. We can go to the second one. So before you just wash off you wash with DI water or PBS in between, maybe wash with DI water before the next solution. So now we'll be doing 2.5 millimolars, right? Yeah. So then you can use Excel or Python or any other tool to just plot and see what is the linear fit, what is the R square value, what is the slope or the sensitivity. The slope will give us the sensitivity. This is 2.5 millimolars. Please make sure no air bubbles or it's covering the entire surface. Switch to the screen. Started. 30 seconds run. Amperometry at 0.7 volts. So at the end of the 4-step calibration, we will actually plot a straight line and we'll see if it is working or not. If not, we'll do it again in the next session. Done. 71 microamps. Switch to the, yeah. So now we are covering it with 5 millimolars, right? So there is no, so you can actually choose the millimolar concentration based on whatever you like. There is no such requirement that you have to go for the same millimolars. You can go for something else also. So you can do in orders of 10 as well, like depending upon what is the range you are trying to detect, you can do it that way as well. And the more number of calibration points you have, the better it is. Okay, so just in the interest of time, we are doing it for 3 or 4. So the first one is just like a control, so 3. But if you wish, you can do more as well. Generally, we would do 5 or 7, and then repeat it 3 times. So we get we know what is the standard error and standard deviation and all those things. This is now 5 millimolar, right? Correct. Yeah. You can save the files as you go. Ready? Screen. Okay, now we are ready to start the third one, which is 5 millimolars, and then the last one, which is 7.5 millimolars. Done? Current value. Rishita, what is the current value? 86. Okay. So you can choose a current value which is when the curve is more or less stable, not at the start. You can keep it running for longer as well. You can run it for 1 minute, 2 minutes, wait for the curve to stabilize. We'll see what we are getting. Ideally, you would repeat this 3 times to get a nice. Nice calibration curve. Let's see what we are getting this time. It's always more fun to do hands-on. We see theory in practice. Yes, last one. Let's see. Then we'll plot the curves in Excel. Ready? Screen. Yeah. Started. So while plotting, you will be using Excel, right? Yeah. Okay. Done. Value 100, 103. Okay. Now we can plot these values in Excel. So you have used the single working electrode, or you have combined all the working electrode together? Single? Okay. So the current may vary depending upon the area of the working electrode. If you use a large area of working electrode, then it will be current is in microamps. So generally we work in microneedles where the area of working electrode is very small. So there the current is in let's say 0.9, 0.8 microamps, in nanoamps range, generally very small. But since this is a large platform, it is slightly larger current we are seeing. Millimolar values are there. Okay. Actually, can you move the values to the center, because you cannot see in the screen on the. Can you move it to the center, please? Just copy it to the center. Yes. What happened? And the units also. Please write the units on the top so that people can see. Okay, now you can plot. Let's have a look at the linear fit. Oh, nice. Looks like a very good linear fit. We can look at the R square value and the sensitivity. Linear fit, please. Linear fit, done. R square is how much? 0.99. Okay, done. What is the sensitivity? 6.12 microamps per millimolar. 6.12. Can you make the font larger, please? That equation, straight line. Yeah, just make it larger, please. So that is the slope of the straight line. The slope of the straight line gives us the sensitivity of the sensor. Make it larger, please. So the sensor is linear in the concentrations that we have tested. So for better, if you were to develop it in the lab, you can go for a larger range of values, concentration. Choose large ones because that is where the sensor is supposed to saturate. You can see what is your linear range. Choose little bit lower also. Maybe you can go into nanomolar concentration also. So that will tell us what is the linear range of the sensor. So the sensor may not be able to detect, let's say, nanomolars, certain nanomolars. We haven't tested that. So you have seen all the steps now. First step is testing or checking the working electrode. If it is fine, then you go to functionalization, where we are doing this electropolymerization. What did we use here for electropolymerization? What type of electrochemical method? Not the chemicals method, cyclic voltammetry. Yeah. So we used, yes, GOX and phenol mixed in PBS. Then third is we actually did stabilization. Then the last one is calibration, which gives us the sensitivity of the sensor. So now it's up to you. We have many more PCB based sensors. Please feel free to come and do it yourself, DIY. Thank you. Yes, who is ready to come? Come. You can come and do it here, no problem. Feel free to use it. No worries. That's the fun, right?